Alright, so we are now in section 6.6. So this is the last section we're actually going to learn out of 6.6. In Calculus AB, you guys should have learned 6.1 and 6.2. We just covered 6.3 and 6.4. We're skipping 6.5, and then 6.6 is not the last section in this chapter, but it's the last one that we're going to learn. So it's about moments, centers of mass, and centroids. It's kind of an interesting chapter, just in this, or in section I should say, just in the sense that it's not super difficult. It's just more like a different type of work. So it's pretty easy actually. Some of the problems take a little bit of time, but it's pretty easy overall. So there's a lot of writing in these notes. I know that I gave you a lot for a Friday, so if you want to take the weekend to finish up the notes, that's totally fine. So it might be a little bit of a long one. So here we go. Mass. From physics, if you've taken physics, mass is a measure of a body's resistance to changes in motion and is independent of the particular gravitational system in which the body is located. So for example, on Earth we measure our weight in pounds, but pounds is actually a force, it's not a mass. So if you divide whatever you weigh by the acceleration due to gravity, you would get how much you actually weigh in mass, not in force. So for example, you have different forces on you on different planets, therefore your mass is the same, but your force would be different since all of their accelerations are different. This first part, center of mass in a one-dimensional system. So it says, consider an idealized situation in which a mass m is concentrated at a point. So for example, if you think of a teeter-totter, right in the middle they have the fulcrum, which is the center of the mass. It says, if x is the distance between this point, mass, and another point p, the moment of m about the point P is m times x, and x is the length of the moment arm. So, for example, if you think of a teeter-totter, and here's the teeter in the middle, if there's a kid over here that weighs, I don't know, 30 pounds, and he's 3 feet away from the fulcrum, and there's a kid over here that weighs 40 pounds, and he's also 3 feet away from the fulcrum. Obviously, the teeter-totter is going to go down on this side because this kid weighs more. But if you move him further away, you can move him to a point where their m times x, their moment, would be the m times x. So x is the distance between the mass, so you can move this kid further away. And then the moment arm. And then m is the mass of the person. So obviously, if you move them further away, you can get the teeter-totter to balance eventually. It says, now imagine a coordinate line on which the origin corresponds to the fulcrum. Suppose several point masses are located on the x-axis. So if you have, like if this is at 0 and you have a mass here and a mass here, you can get all these masses to balance and you can figure out where the balancing point is going to be, and that's what we're essentially trying to figure out. So it says, suppose several point masses are located on the x-axis. The measure of the tendency of the system to rotate about the origin is the moment about the origin, so it's called the moment. And it is defined as the sum of the end products mi, xi, where x is the distance from 0, or actually just the position, I should say, and then m is the mass that you're hanging from that part, or placing at that part. So m sub naught is m1 times x1 plus m2 times x2 plus ... all the way up to however many there are. If m naught is 0, the system is said to be in equilibrium. That's two words, sorry. It's not in equilibrium, it's in equilibrium. So if it's centered right at the 0, then obviously it's in equilibrium. It says, for a system that is not in equilibrium, the center of mass is defined as the point x bar at which the fulcrum could be relocated to obtain equilibrium. So if you moved the center of mass, that would be the new equilibrium point, and it's notated by this x bar. It says, let the point masses m1, m2, all the way up to mn be located at these different locations. The center of mass is x bar equals m naught divided by m, where m is the summation of all the masses, so however much all the masses weigh together. And that's the total mass of the system. So obviously there are more notes on the back, but actually for right now, what we're going to do is we are going to look at some examples, just so we can kind of split it up and you guys can see how we would do these types of examples. So the first one we're going to look at is example number 1 in your book, so go ahead and look at that one. Alright, so the first example says, find the mass in slugs, which is what we calculated here on the Earth, of an object that weighs 1 pound. So, for example, if you remember the force equals mass times acceleration, if I know the force is 1 pound and I'm looking for the mass, I can solve this equation for mass and get force over acceleration. So I know that the force is 1 pound. Remember that pounds is a force. And acceleration on Earth due to gravity is negative 32 feet per second. So we can just divide it by 32 feet per second squared. And if you divide that, you should get 0.03125 slugs. And they define that because it's equal to 1 pound, or it's the proportional slug amount to 1 pound. This is called a pound mass. So that's just an example of how to convert from a force to a mass. So if you, whatever this object is that weighs 1 pound on Earth, if you put it on a different planet, it would still be 0.03125 slugs, but depending on the acceleration on the other planet, it would weigh a different amount, or have a different force, I should say, acting on it. Let's look at example 2. Alright, so this is example 2. You can kind of see the little chart from the book on page 456. So it says, find the center of mass of this linear system. So remember that the center of mass is equal to x bar. Oops. X bar. And x bar is equal to m naught divided by m. So remember that m is the summation of all the masses. So if you added up all those masses together, you would get 10 plus 15 plus 5 plus 10. And I'm getting those from right here. That's the weight of the masses. And then m naught is if you multiply its position, which is x, remember the distance, or the position on the number line, I should say. So the distance, which is x, times the first mass is 10, plus the position of 0 times the second mass is 15, plus the position of 4 times the third mass of 5, plus the position of 7 times the last mass of 10. So if you simplify on the top, that would equal 40. And if you simplify on the bottom, you also get 40. So if you divide 40 by 40, that equals 1. So that means that the center of mass of this system is right here at x equals 1. So if I made that my fulcrum, the teeter-totter would balance, essentially, is what that is saying. So that's the center of mass, where all of the mass is in equilibrium about that point. Alright, if you look at the back of the notes paper, you'll see the center of mass in a 2-dimensional system. So the last example we just did was in a 1-dimensional system because we were only looking at the x-axis. But you can also look at it in a 2-dimensional system where you have an x and a y. So it says, let the point masses m1, m2, to mn be located at various coordinates in the coordinate plane. It says the moment about the y-axis is my. So notice here, it's kind of an opposite way of thinking, I guess you could say. But notice that you have the m1, x1, m2, x2. So even though we're looking at my, the moment about the y-axis, you're looking at it with the mass times the x-coordinates. So keep that in mind as we go through. So it's the opposite. It's the m of y, but it has the x values with it here. So notice that. And then vice versa, with the m of x, the moment about the x-axis, it has the y values, or the y coordinates. So it pairs the opposite ones together. So the center of mass is located at x bar, y bar, or the center of gravity you can also call it. And x bar is m of y over m, and y bar is m of x over m, where m is still the summation of all the masses. So let's look at an example for this one. Alright, so here's the next example. It says find the center of mass. Here are the different masses, 6, 3, 2, and 9, and they're located at these 4 different points. I took a picture of it as well. I know it's kind of hard to see, but there's also a point over here in the corner at negative 5, 3. That one's the mass of 2. So we have to do, the center of mass should be a coordinate. So if we look at the coordinate, remember that for x bar, let me write this out, x bar equals my, remember it's the opposite one, over m. So my says to take all of the masses and multiply them times the x-coordinates and add them together. So a mass of 6 with 3, mass of 3 with a coordinate of 0 for x, a mass of 2 with a coordinate of negative 5, and a mass of 9 with a coordinate of 4. And you divide that by the summation of all the masses, so 6 plus 3 plus 2 plus 9. And when you simplify that, on the top, you get 44. And on the bottom, you get 20. So 44 over 20, when you simplify that, you should get 11 over 5. So that's the x-coordinate. If we look at the y-coordinate, y bar, it would be mx, the moment around the x-axis, divided by m. So the mass 6 times the y-coordinate of -2, plus the mass 3 times the y-coordinate of 0, plus the mass 2 times the y-coordinate of 3, plus the mass 9 times the y-coordinate of 2. All of that divided by the same summation, which would be 20. If you simplify that, you should get 12 over 20, which simplifies to 3/5. So our center of mass is at 11/5, comma 3/5. Sorry, that's kind of messy. So 11/5, comma 3/5, that's a little bit over 2 and a little bit under 1. So a little bit over 2 and a little bit under 1 is probably going to be right about there. So if you look at that picture, that center of mass is probably somewhere right about there if you consider all of the masses that are in the picture. All right, good. So that's a center of mass in a two-dimensional system. The last part of today is the center of mass of a planar lamina. So if we look at that one, a planar lamina is a thin, flat plate of material of constant density. So the density is a constant, and density is a measure of mass per unit volume. So normally we talk about like the density of water or whatever, so it's how much mass it has per volume. However, for planar laminas, because they're thin and flat, we don't really call it as volume since they don't really have much of a height. So in this case, we're going to consider density to be mass per unit area. So we're just looking at the area. And density is denoted by the Greek letter rho, and it looks like a P kind of, but it's called rho. So here's where calculus comes into play, because so far we haven't really looked at a lot of calculus in this lesson. It says let f and g be continuous functions such that f of x is greater than or equal to g of x, so that f of x is the function on top, on some continuous interval from a to b. And consider the planar lamina of uniform density rho bounded by the graphs of y equals f of x and y equals g of x. So it says the moment about the x-axis is given by m of x equals that formula, so go ahead and write that down. And the moment about the y-axis is given by m of y with that formula. So they're similar formulas and they're different. They both have this f of x minus g of x piece to them. Excuse me. Whereas this one, excuse me, I'm so sorry. This one has x in it, and this one has the average of the two functions in it. So that's what's different about those two. All right, so the center of mass x bar, y bar is given by x bar equals my over m, just like in the last one, and y bar equals mx over m, just like in the last couple examples. And here's what m is equal to now. So it's not a summation of simple numbers anymore. Now it's actually an integral. And it looks very, very similar to the moment about the y-axis. The only thing is that it doesn't have that x in front of it. So write down those formulas. We'll do a few examples with this one. All right, so here's example number 4. It says find the center of mass of the lamina of uniform density. So here's this lamina they're talking about. It's this pink shaded region. So it has very little thickness, which is why we're talking about area and not volume. So it has uniform density rho, so it's all the same density all over, and it's bounded by the graph of 4 minus x squared, which is the graph of that parabola, and the x-axis. So what we need to figure out is we need to figure out the x value and the y value that we're looking at. That is the center of mass. Now, if you notice, this parabola is actually centered on the origin as far as over the y-axis is concerned. So the center of mass in the x direction is actually just right in the middle at 0. So we know that x equals 0 is the center of mass. So we then know that x bar automatically, we know that x bar equals 0 because of its symmetry. Symmetry about the origin. So if that ever happens, you automatically know what that is centered around because it's automatically symmetrical. So obviously it's going to have the same weight on both sides, so its equilibrium point will fall right in the middle. As far as y bar is concerned, that one's a little bit different. So if you look back at y bar, we know that y bar is equal to mx over m. And we have two formulas now. We have one for mx, we have one for m that we need to figure out. So let's figure out mx first, and then we will go back and figure out m. I know it does it a little differently in the book, but that's okay. We can switch it up a little bit. So to find mx, let's use our formula that says, and if it's okay with you, I'm going to erase some of this stuff. Alright, so to find mx, it's rho times the integral from a to b, which in this case is -2 to 2, because that's where the graph intersects the x-axis, so from -2 to 2. Then the next part of the formula says that it is the average. Remember, it was f of x plus g of x divided by 2. We said that it was the average of the two functions. Well, in this case, g of x is 0, so the average would just be f of x plus 0 over 2, which is just f of x over 2. And if you actually look at this picture, it shows you kind of how that's illustrated here. Because we're going to be taking an infinite amount of rectangles here, if you can see this little blue rectangle. And so f of x over 2 is essentially, if you take the distance from the x-axis to the top and then cut it in half, it would be the center of that rectangle. And if we take rectangles all over this, if we integrate that, we can find out an infinite amount of rectangles, and we can find the center for each one and multiply it obviously times the mass to get what the center of that one would be as well. So if I can erase all of that. So f of x over 2, which is actually f of x is just 4 minus x squared over 2. And then times, the rest of the formula says to multiply that times f of x minus g of x, which is just 4 minus x squared dx. So I can factor out a 2, so I'll get rho over 2 times the integral of 16 minus 8x squared plus x to the 4th dx. And if I integrate that, I get rho over 2 times 16x minus 8x cubed over 3 plus x to the 5th over 5 from -2 to 2. And if you plug all of that in, you get that the m sub x would equal 256 rho over 15. So that's m of x, or m sub x, is 256 rho over 15. So make sure you have that copied down. I'm going to erase some of this just so that I have room to do the next part. So 256 rho over 15. So that's m sub x. Now we need to go back and find m. And if you look at the formula for what m would be, you get rho times the integral from -2 to 2 again of f of x minus g of x, so 4 minus x squared dx. So if we take the integral of that, we get rho times 4x minus x cubed over 3 from -2 to 2. And if you plug in -2 and if you plug in 2, you should get 32 rho over 3. And I'll let you check that to make sure that that works. So, to find y bar, again, we already know that x bar is 0 because of the symmetry. To find y bar, we divide m sub x, which is 256 rho over 15, divided by m, which is 32 rho over 3. And if you divide those, you should get 8/5. So that means that the center of mass is at 0,8/5. So about 0, maybe, let's see, that's about 1.5, a little bit more than 1.5. So it's about right here. That's where the center of mass is of this planar luna, or lunar plana. No, planar lamina. There we go. Not luna. We're not talking about the moon here. Alright, good. So that's example 4. We're going to do one more. We're going to do example 5, and then that's it for this section. So let's look at example 5. Alright, so this one is our last example, example number 5 on page 460. It says find the centroid of this region. So you can see the little planar lamina in pink right there. And so this one is not symmetrical at all, so we're going to have our work cut out for us as far as figuring out where the x bar is and what the y bar is. So let's start with x bar. So well, first let's figure out the mass, since we're going to use it in both of them. So we're going to figure out m, which equals, excuse me, well, okay, let me put it this way. Alright, so this would be rho times the integral from, if we figured out, I mean, obviously if you didn't have a graphing calculator, you would have to figure out where these two graphs, intersected on your own. But you could easily do that with by setting the two equations equal to each other. So 4 minus x squared equal to x plus 2, and you could figure out where they intersected, which is at negative 2, 0, and 1, 3. So it's from negative 2 to 1 of f of x minus g of x, the integral of f of x minus g of x. So that would be 4 minus x squared minus x minus 2. So it's 4 minus x squared minus x minus 2. So that actually becomes 2 minus x squared minus x if you combine ahead of time. Dx. And if you integrate that, you get 2x minus x cubed over 3 minus x squared over 2 from negative 2 to 1. And if you plug in 1 and you plug in negative 2, you should get that this is equal to 9 rho over 2. So we know that the mass is equal to 9 rho over 2. We're going to be using that in both x bar and y bar. So keep that in mind as we go through. 9 rho over 2. So I'll actually write it up here at the top so that we have it on file. So m is equal to 9 rho over 2. Alright, so for x bar, we're going to do my divided by m. So we already know that m is 9 rho over 2. To figure out my, remember, we need rho times the integral from negative 2 to 1. Oops, there we go, to 1. Now for this one, remember that it is the x times f of x minus g of x. So x times f of x minus g of x, which we already discovered, is, from the last one when we were just doing the mass, we figured out that it was 2 minus x squared dx. So that would be rho times the integral of 2x minus x squared minus x cubed dx. And if we integrate that, we get rho times, well, actually not the integral, it would be parenthesis, 2x squared over 2, which is just x squared, minus x cubed over 3, minus x to the 4th over 4, from negative 2 to 1. And when you simplify that, you get negative 9/4. So I kind of jumped ahead up here. I didn't need that divided by m yet. So that's just my. So now to find x bar, you do my divided by m, which is negative 9/4 divided by, negative 9 rho over 4, divided by 9 rho over 2. So when you simplify that, you actually get negative 1/2. So we know that x bar is at negative 1/2. So let me make a note of that up here. X bar equals negative 1/2. Alright, and then last but not least, we need to know m of x so that we can figure out y bar. So m of x is rho times the integral from negative 2 to 1. And remember, this one's the average of the two, so you have to add them together. 4 minus x squared plus x plus 2 divided by 2, which ends up being 4 minus x, I'm sorry, not 4. 4 plus 2 is 6. So that's 6 minus x squared plus x divided by 2. So that's the f of x plus g of x divided by 2 part. And then times f of x minus g of x, which is 2 minus x squared minus x dx. So if I pull out a 2 from the beginning part, I get rho over 2 times the integral of, if I multiply all of that together, I get x to the 4th minus 9x squared minus 4x plus 12 dx. And I urge you to check that work just to make sure that you understand where we're getting these from, but I just pretty much multiplied. Once I took out that 2 and put it out to the front, it went there. Now I just multiplied 6 minus x squared plus x times 2 minus x squared minus x, and you should get what I just put down there. So when I integrate this, I get rho over 2 times x to the 5th over 5 minus 9x cubed over 3 minus 4x squared over 2 plus 12x. And that's from negative 2 to 1. And if you simplify all that, you should get 54 divided by 5. And so for y bar, it equals 54 rho divided by 5. And so for y bar, it equals 54 rho divided by 5 divided by m, which is still 9 rho divided by 2. And if you simplify all that in a calculator, you should get 12/5. So the center of mass is at negative 1/2, 12/5. Which you can obviously see from right there in the picture. That's where the center of mass would be located. Alright, so that's it for today. I'll give you guys some homework. Like I said, if you don't finish this in one sitting, that's fine. We'll just have it finished by next week. One thing I do encourage you to do, by the way, is look at example 6 in your textbook on page 460. It's not too difficult to understand, and that's a good one to look at for a simple plane region. So go ahead and do that for me as well.